Okay, people, this is probably the first view to a reasonably large public. One or two people have seen this, but the first view to a large number of people. Expected soon. This process takes time. I need to proofread, send it back. They'll proofread, send it back, and so on and so forth. It takes a lot of time because I'll have to go through every word and things like that. They've done a decent job in terms of converting whatever I sent, but I need to change whatever I said. So, few few words. I realize that it may make some other sense which I cannot afford, and so on and so forth. It has to make whatever is exactly meant. Uh, I I was just correcting something where it said the dyes APF and HBF can be used to measure hydroxyl radicals. I'm just on that chapter. And then I realized if I say and, would it be interpreted as both are needed at the same time, and so on and so forth. So it takes a lot of time. By the way, this cover was designed by one of our PhD students, Janani Venkatraman, who works in Nitish Mahapatra's lab. And the publishers asked me whether they're going in for the cover. They asked me whether do you have any attractive image that can be used as cover. Then I asked around, we couldn't find any that was attractive enough. To begin with, we didn't have many images, and then I asked all my students who have been in the lab over the past decade. We couldn't find any. So then Pallavi came and said, Janni is artistically oriented. Shall I ask her? I said, yeah, definitely. But then I asked her, then we talked. And then this is the first book cover that Janni has designed. I liked it. I liked it a lot. I think it communicates at different levels. Of course, her thing is the picture. Okay, the text is the publishers. They put the text on top of it and sent it. The story was, I said, fine, ask her to get in touch with me. And that took time because I guess artists work at their own pace. And I guess she was also busy. So, for the first meeting, that is, took time. About 3 weeks later, we met online. And then we talked about it. Yeah, the way she was approaching it, I seemed to be in sync. Said, try it out. I'll definitely make sure that I give you credit in my preface as well as separately in the book. It will be mentioned somewhere that you designed. That's the only thing that I can do. She said, yeah, I've also not designed any book covers. So we tried. The first image was this. I liked it. I really liked it a lot based on the very small brief that I'd given. Of course, I'd sent her the book, the small blurb that I wrote about the book and so on and so forth. So that she had seen. And then I sent it to the publisher saying that our student designed it, see whether you can use it. Otherwise, they were going to design their own thing. She liked it a lot. Sandhya Devi, she World Scientific. She liked it a lot. It was great. We'll go ahead with this. That was it. So Janani Venkatraman will be acknowledged for her contribution to the cover. I mean, it's her cover, it's her image, and then this thing comes on top of it. So they designed two different covers where the placement of the text was slightly different in the second cover, and that's how it is. So this hopefully should be available in a few months, and the videos for this course will become available only after this comes out. That's the deal that I have with NPTEL. Otherwise, I asked them to record it the next year because I said, this is coming out, I cannot afford any copyright issues. They said we won't, we won't put it up on the portal. And to make sure that I haven't even edited the videos as yet, I'll edit them later and get it ready and so on. So this is the first view for a reasonably large public. Okay. Pardon? That's up to you. Thank you. But it's very pretty, very, very nice. Anybody who looks at it says it's nice. It's attractive because that matters for a book. It is not, rather, at this stage, we don't expect volumes. If that's the reason why some of these big ones were, I thought may not be interested. I didn't even approach them. See, my first book was published by Springer Publishing. My second book was more prestigious, Oxford University Press. And but this volumes, I was not sure. They go by how many copies they can sell and so on, how many downloads they can have and things like that also, apart from the basic material. So I didn't even approach them. And these people approached me. When they approached me, it was a little too early. Did I tell you that story? No? Okay. It was a little too early. 2019, they approached me. And as with many people, many publishers keep approaching. So here, it was a very open kind of a thing. So something struck me, this might work out and so on and so forth. So I had some plans, but I had plans closer to my retirement, which is 2029. So I thought I'll write some 3 years before the thing, and that way publish the book, get out of this place. That is what I thought. And then this thing came. So I wrote to them, this is what I'm planning, but the work is still on. And then they immediately wrote back saying, yeah, we'll take it up. And then I asked them, what's the longest you can give me? They said maximum 4 years. I said, fine, I'll take 4 years, because the work was still on. A lot of work was still on. It was a research monograph. It is a compilation of my research work, and which will come next in the course also. And then wrote this up. It took my 4 years. In fact, the last chapter got published some months ago. So it took so much time. The work is still on, but it has taken a slightly different turn now, a more applied turn. That's so there's some nice completion and so on and so forth to this. So wrote this up. This thing. Where is the blurb? Okay, this is mechanism. It doesn't work. The new tab doesn't work. So these would be the table of contents. Relevance and importance of reactive species. Okay, I need to. Analysis of reactions that involve reactive species, measurement of reactive species levels in biological systems, reactive species in cell signaling. And then our work starts. Reactive species in oxygen supply, inoculum, RS induction to improve bioreactor productivities, reactive species and other stresses, reactive species aspects in nanobiotechnology, reactive species in cancer treatment and management, and a reactive species module for integration into any metabolic network or into metabolic networks. This is the one that took 14 years and got published. First paper got published a few months ago. Subhashri, who put that work together of 14 years, would be defending her thesis next week. So I think next Friday or something. Hopefully next Friday. We'll see. It's not fixed as yet. That is what it is. Okay. Okay. Get rid of this. Coming to whatever we're doing, we're looking at electron paramagnetic resonance or electron spin resonance spectroscopy, EPR or ESR for this course. We're going to interchangeably use the terms. And as mentioned towards the end of the previous class, Zavoisky discovered the principle 1945, and biological samples were studied within 10 years of that, which is quite fast. And then we said that it can measure only the ones with a free unpaired electron, an unpaired electron, because it depends on the paramagnetism. if there are paired electrons, then the spins are opposite and they cancel each other, and so it cannot do a diamagnetic species. It has to do a paramagnetic species, which will arise only if there is an unpaired electron. The classical idea is something like this. So the quantum idea is different, and there are more evolved thoughts on electron, where you can find an electron. It's a probability of finding an electron, and so on and so forth. We are not getting into all those. I'm going to say that the electron goes like this around the nucleus. Okay, that's a classical view. It is incomplete, yes, but it helps you somewhat understand the principle. Any manipulation, you will need a quantum view. So the unpaired electron has a spin which has, it's a charged particle spinning, therefore there is a magnetic moment associated with it. You all know some electrical engineering. So this is the situation. To this situation, if you apply an external magnetic field of field strength H, the unpaired electron can align itself with its spin magnetic dipole moment with or against the applied applied external field, the magnetic field. Okay. Excuse me. So this is what happens, and the basis for the measurement is something like this. The energy states associated with either with the magnetic field, alignment with the magnetic field, or against the magnetic field are different. The parallel orientation with the magnetic field has a lower energy compared to the anti-parallel orientation typically. The difference between those two energies are something can be calculated as follows. Delta E, the difference between those two energy levels, is a product of something called G, okay, times beta times H. G is the spectroscopic splitting constant, which happens to be a universal constant. Okay, it is something like your G value for gravitation, gravitational attraction energy, and so on and so forth. Not the acceleration due to gravity. That's not a universal physical constant. There are a few of these universal physical constants that won't change. The charge of an electron will not change, right? Those are universal physical constants. So similarly, the spectroscopic splitting constant is 2.00231927 for an electron, which is a universal physical constant. H is the applied magnetic field strength, and beta is something is again a constant, but not a universal constant. It's a constant called the Bohr magneton, and its value is 9.274 into 10 power minus 4 joule per Tesla per particle. And for most lab measurements, the difference between energy levels is 10 power minus 3 kilocalories per mole. So do you know the energy levels associated with chemical reactions? Oxidation of glucose, something like that. Or the order of magnitude is what I'm looking at. Do you recall the kilocalories per mole value associated with any chemical reaction, typical chemical reactions? Oxidation of glucose is on the higher side, but order of magnitude maybe higher by 1 or 2 orders of magnitude. But do you know the order of magnitude associated? Here we are talking of 10 power minus 3 kilocalories per mole. Any guesses, any recalls? No? Insignificant compared with the energies associated with chemical reactions, which are typically about 10 power 3. Sorry. Where? Okay. 10 power minus 3. Check up, can somebody look up the energy associated with glucose oxidation? 180 kilocalories per mole, if I recall correctly, under some conditions, of course. No, 180 is the molecular mass. Some kilocalories per mole, hundreds of kilocalories per mole. Kilojoules, yeah, it could be kilojoules. Any number? The the enthalpy of the reaction. I mean, start with enthalpy. Enthalpy. Delta H of the reaction. Oh, that is where the confusion was. What is that for glucose? Kilojoules per mole. Divided by 4.2, you will get, divided by 4.2, you will get kilocalories, right? 686 yeah, that's right. 686 kilocalories per mole. Okay. So this is 10 power minus 3. So that is about 5 to 6 orders of magnitude higher. Glucose, of course, is on the higher side, but any typical reaction is about 10 power, about 10 power, at least 10 to about 100 is very common, and so on and so forth, kilocalories per mole. Okay. So this is about 5 to 6 orders of magnitude less than the energy associated with chemical reaction, the energy that gets released during chemical reactions. So insignificant compared to energies associated with chemical reactions. And when an energy equal to the difference between the energies of the two orientations, which is what we are represented as delta E, is provided by some means, then the electrons which are aligned with the field will absorb that energy and move to the higher energy level, because the energy is quantized. That exact, if you irradiate it with that exact energy which equals the difference between these two levels, then it will go to the higher level. Falling down is spontaneous, but going up to the higher level, you need to provide it with that energy, that exact energy difference between the two levels. Okay. So this is the basis. Okay, let me finish this slide. When you do this, the matching occurs. This matching is called resonance, as you all know. Okay. And when the matching of energy occurs, you know that even disasters can arise. The Tacoma Bridge disaster is a very common example that is given. The frequencies matched, and that led to huge sways in the amplitude, and that led to the collapse of the bridge at that time. So resonance is essentially a matching aspect and whatever consequences that arise out of that matching. In this case, we are matching the energy difference between those two energy levels, alignment with the field or alignment against the field. And transition from the lower to the higher energy states occurs with the net absorption of energy. And what EPR spectroscopy typically does is measure this energy that is absorbed, which could be of the order of 10 power minus 3 kilocalories per mole. Okay. With this measured energy, we data process and get whatever information that we need in EPR. This is pretty much the principle in NMR also, but the way of processing and things like that is different. We will stick to EPR in this course. Okay. So this is the basis. Any quick questions? Okay. If not, I'll give the class to Radhika. She is going to conduct a game. Okay. People who have done the transport course know all about the games and so on. People who have not done courses with me, this is for the benefit of other people also. I need to say this. We design games to help you learn better, essentially. So you play it with all competition, right? You bring in all your competitive spirit to this game, right? And feel kicked and elated if you win it, and so on and so forth. All that we do. We'll also egg you out, egg you to do well. It's a competitive sport. Okay, only this part of the course will be a competitive sport. Learning is not a competitive sport, in my opinion. Okay, but competitive sport has its own attraction. Competitive spectator sport has its own attraction, right? So I'm just utilizing that to make you learn better. We'll revisit things. You don't need to prepare for this, and so on and so forth. You have fun, play, right? And let us see who wins. That's it. No marks, nothing, as you all know. So I'll give the class to Radhika. I just need to open up your Moodle page.
So good morning, everyone. So myself Radhika, I'm the PhD scholar under K Suraishkumar sir. So I'm the TA for this course. So, under the guidance of K Suraishkumar sir. Okay. Okay, I'm the TA for this course. So today we'll be playing this crossword game. So in this game, we'll be having some 14 questions. So these questions are the basic recap of your reactive species. So these 14 questions will be like across and downwards. So if you're answering correct, it will be like highlighted in green color. And if you're answering wrong, it will be in the red color. So you can discuss among yourself and refer your class notes and answer the questions. You can start the game. Yeah, let's see who finishes. Sir, only if they tell we can know, sir. So since we cannot see this, the leaderboard is not there for this. Okay. Yeah, next time. Okay. No, no, you don't need to upload it. So your good name Abbas and your name Yashwan. Okay, you both are the first one to complete. You want other Vikas is the second, goes to the second place. Okay. Group, it's a group teamwork. You're done. Your name? Lakshman. So you played individually. Nice. Okay. No need. Abman. So Abbas team is the first one and Lakshmanan is individual player. You are also team player. So you have another 10 more minutes. 8 minutes. Okay. Okay, 5 more minutes. Okay. So the first question is act as an aging clock in every cell. Oh, sorry, sir. Forgot. Okay. Progressive genetic disorder that causes children to age rapidly. Okay. Third one. So dash species is a common term for both free radicals and reactive oxygen species. Yes. Yeah. Fourth one. So era is the aging of mammal. Cenozoic. Okay. Delays or prevents oxidation of substrate. Yes. Antioxidant. Sixth one. So dash stress occurs when the free radicals and the antioxidants are out of balance in the biological system. Oxidate. So this is it's a drink of happiness that was originated from the ancient Indian Somras. And eighth one is, so collective term that includes oxycross. So dash radical is any species capable of independent existence that contains one or more unpaired electrons free. So single gene mutation of a type A dash protein is responsible for progeria. It's lamin. 11th one. So name of the resultant product of one electron reduction of dioxygen is superoxide. Dash principle state that electrons fill low energy atomic orbitals before filling iron of Bohr. Dash radicals are generated from thiols. Style. Next one. So progressive physiological changes in an organism that leads to senescence or a decline of biological function. Yes. Yes, sir. Team 1 is Abbas team. One more is there. Okay, one more thing, yeah, sixth one. So dash 6 occurs when the free radicals are not oxidated. Oxidative, no, oxidation. Sixth one is oxidative. This is oxidation. Okay. So the first place goes to Abbas team. And the second one goes to Ankita. And the third place goes to Suchitra and Jayashree. They all together seem as a team. Yeah, they were with the team. They are the part of the team. Yes. So I hope you all enjoyed this game. Yeah, one of the. Yes, sir. Thank you, sir.